Sorry, the meeting controls are done. Okay.
Hello?
Hello?
Okay, so you can hear me, right?
Yes, you can.
Okay, finally.
Okay. You share recording. We're recording, right? Yeah, okay.
Sorry.
That's fine. Yeah, we can start.
Okay, everybody, I'm sorry we are late because technical problem. Today, our first speaker is Siyuan from McMaster University. Oh. Hello, everybody. I'm sorry we are late today because of the problem. So, our first speaker is Siyuan from McMaster University. His topic is Rigidity of Riemannian Penrose inequality with corners. So let's work.
Right. Thank you everyone for coming and also online. So the seminar is a low regularity physics and geometry seminar. So, well, in the last 2 years, I was working on high regularity. So today's talk will be not the new stuff, but like 2 years ago. Okay, but there are still open questions and lots of problems relating to this topic. So I choose to talk today here. Okay. Okay, so we're starting from some basic surface theory and also from general relativity, and now we'll talk about the main result and also talk about some open problems. So first of all, I will always use these slides to describe what we learned in differential geometry of surface. So basically, when you write down a surface, and you can write down your position vector, and then you can compute your first fundamental form, and also second fundamental form, and more importantly, you can compute the Gauss curvature. Okay, so here, the Gauss curvature here, we compute use this Hij and Gij. This is actually called the Gauss equation. Sometimes we write the H up and the lower J, which means the normalized second fundamental form, but because this is 2 dimensions, so it's the same as you write the determining. Okay.
Sorry, what is the X? What's the X subscripts?
Oh, so this is a second derivative you can write down. So if this is just X is a position vector, so I and J you can write down as. All right. Okay, so a basic theorem, which is a uniformization theorem, tell us, okay, you can describe your surface into genus. You characterize your surface into genus. In particular, a convex surface, then you have to be a topological sphere. You can't have any genus at all. And now, and also because it's convex, so it has positive Gauss curvature. Okay? So basically, you have this convex surface had to be S2G with positive Gauss curvature. So the other way around is, now if you consider arbitrary surface, you say S2G, so this is a Riemannian manifold, 2 dimension, and because your Gauss curvature is intrinsic, so you can compute just by the metric. So now this is the intrinsic one. So the question is, can you realize this as an extrinsic one, which is convex surface in R3? So note that here we have 2 kinds of things. So the first thing is intrinsic. So this is intrinsic. Okay. So now the other one is convex surface in R3. So this is R3. So this is convex. So this is intrinsic. This is extrinsic. Okay. So the uniformization theorem says this is this way. Okay. So anything like this, you have to be this. Okay. So the other way around is you can have this one. Right? So this is a question. So I wrote that one. That means it's a theorem. Okay. So this is actually called Schwarzschild embedding problem, and then this is proved more than 60 years ago. Okay, by Nirenberg and Pogorelov independently. So from the analysis point of view, here you have to make some regularity requirement. So here you have to be a C4 metric on S2. So here, this theorem here, what I state is a form in the Nuremberg form. Okay. So now you have positive Gauss curvature, then it can be a symmetric embed into R3 as a convex surface. So this is the existence theory. Okay. So you actually also have a uniqueness theorem. Okay. So uniqueness, now you have existence, but the thing is, how many embedding you have, right? So probably you have S2G, but you probably have different kind of embedding. So if you have different kind of embedding, are they the same or not, right? So this is uniqueness. Uniqueness says if you have two embeddings, okay, so if they are convex or symmetric, then they have to be unique up to rigid motion. Here we identify the orientation so that they have the same orientation. Otherwise, reflection is another one. Okay, so here you only have translation and rotation. Those are rigid motion of R3. Okay? So this is a conversion theory. It's actually proved earlier than Nuremberg's existence theory. Okay, so here we have existence and uniqueness. Okay, so existence and uniqueness, then we have one-to-one corresponding. Right? So one is S2G with positive Gauss curvature. This is intrinsic, and the other is a convex surface in R3, which is extrinsic. Okay, so the remark would be, unlike the existence theory, okay, so existence theory is highly restricted because if you want to high dimension, then you will have, yes?
I was just wondering, I don't know if the people online can hear, but when you say convex surfaces, is there any assumption that they are, I'll ask it again tonight. So I was just wondering, when you say convex surfaces, is there any assumption that the surfaces a priori are like bounded?
Oh, yes, they are bounded, close bounded,
Okay,
close
okay.
bounded smooth. Okay.
Okay, thank you.
Otherwise, it can be close on S2, right? Okay, so here, any more questions? Okay, so the uniqueness actually works for high dimensions as well as in space form. Space form here, I mean, upper hemisphere and the hyperbolic space. So those are with simple topology. Okay. Okay. So those are all those Euclidean space. Okay. So I did not really talk about the existence theory for hyperbolic space and anything else. So, but I want to talk about the Schwarzschild, which actually is different phenomenon from the Euclidean space. Okay. So Schwarzschild, we say sometimes we say spatial Schwarzschild manifold, or sometimes we just say Schwarzschild manifold. Depends on where your background is. Okay. So for me, it's a manifold with a metric in this way, which I wrote as GM. Okay, so now you see this is ds squared, but before that you have a warped, which is 1 over 1 minus 2m over s. Okay, so obviously, if you want this is a metric, then your s, okay, so your parameter s has to be greater than 2m, otherwise it's not a metric, right? So this
is a positive definite.
Yeah.
So it's the Riemannian case. It's not Lorentzian.
Yeah, no, this is a Riemannian manifold. It's not the Lorentzian.
Probably it's the space-like
Sure.
slice.
Yeah. Sure.
You just get a slice. Okay, and also we are talking about the physical natural one. So we are talking about the positive mass m is positive. So you can have the negative mass one, but that's not complete manifold. Okay. So a theorem proved by Li and Wang is saying the following. So now you just consider the coordinate sphere, okay, nothing else, okay. So then they can prove that very, very close to that coordinate sphere, then you can have another surface, okay, which I wrote as sigma 2, okay. They are asymmetric, which means their induced metric are the same, but their second fundamental form are different, okay.
Wait, the convex surface now is in R3 or what? Sigma total.
Both are in Schwarzschild domain.
So both are in the first.
Yeah. So basically, I'm writing, okay, so Schwarzschild, we always write in this way, okay. Okay, so this is MM. As we see, so this is you have boundary. Okay, so the boundary is just s equal to 2. Basically, just s equal to 2m. Okay, so because of Schwarzschild manifold, so s has to be greater or equal than 2m. So this is a boundary. It's actually a totally geodesic surface or minimal surface. So now you have a sigma, which is here. Okay. So this is a coordinate sphere. Okay. So you can perturb a little bit. Okay.
So sigma is itself. So what does convex mean? Convex means positive definite second fundamental.
Yes.
And so sigma is it not itself convex?
Sigma itself is also convex.
Oh, it is. Okay.
Yeah. So you can compute it. You can compute the principal curvature of this coordinate sphere. It's I believe it's S over 1 or S prime over something. It's just using those S, and it's quite clear to compute. Okay, so now you have this sigma 2. Okay, so both of them convex, which means they are second fundamental positive definite. Okay, and they are asymmetric, so the induced metric are the same, but their second fundamental form are not the same. Okay, so if your second fundamental form are not the same, obviously you can't recover it using rigid motion of the Schwarzschild manifold. Actually, the Schwarzschild manifold is here. The rigid motion is just a rotation, so you can't really rotate in any case back to the coordinate sphere. So the reason here is the hidden reason here is actually simple. So the rigid motion in Schwarzschild manifold, you only have 3 dimensions. You only have rotation. You don't have translation. Okay, in R3 you have translation. So now you give a three dimension freedom. Okay, to do the those existence theory. Okay. Okay. So now question is, okay, so now I know that even in the best case, the coordinate sphere, I can't guarantee a rigidity of a symmetric surface, right? So I have to impose something. Okay.
Sorry. And sigma tilde can be arbitrarily close to sigma or no?
You actually have a lot of sigma tilde. It is close.
So you don't even have local region.
No. So you have to impose some condition on this okay? So what is a natural condition to impose, right? So this is a very natural question. Okay, so well, this is one motivation. Okay, so the other motivation is actually from a study of Riemannian Penrose inequality. Okay, so basically now we have a manifold which is asymptotically flat.
Excuse me, I have a question.
Yeah.
So if you go back one slide, let's see here. So I'm curious as to what you mean by rigidity of what do you mean by rigidity in this sense, in the Schwarzschild sense? Like I can understand it in the Euclidean sense, but in the Schwarzschild sense, I'm a little
in the Schwarzschild.
Yeah.
So basically, what I want to say is, so if you have two surfaces, okay, in Schwarzschild manifold, they are asymmetric to each other, okay.
Okay.
So in Euclidean space, they are the same, right? After rigid motion. But here we know you can't, right? Because we have examples.
Yeah, because of Li Wang, you're saying that.
Yeah, because of that. So you need to impose something to exclude Li Wang's example, right?
Okay, I think I see.
Okay.
Thank you.
Thanks. All right. So now our second motivation is from Riemannian Penrose inequality with corners. Okay. So before that, we need to talk about what is PMT, and then we talk about So we say a manifold MG is asymptotically flat, then we need to have impose an order. Okay. So basically, how fast it decays to Euclidean metric. Okay. So which is in the following. Okay. So now, if your delta, so decay order is greater than half, then Bartnik proves that the mass is well defined, which is ATM mass, which is the following. Okay. So we will not go deep into this part. We just review some results of PMT. Okay. So the fundamental theorem by Xiong Yao and later by Witten says if MG is an asymptotically flat manifold with non-negative scalar curvature. Recall here we don't have boundaries. Okay, so here we are saying this is a complete no boundary. Okay, then your ADMS greater or equal to 0. Okay, and equality holds if and only if it's asymmetric to the Euclidean metric. Okay, so in the last probably 5 years, we have several more, okay, proof for this positive mass theorem. Okay, the first one coming in 2018, actually I think it's earlier than that, is by Yu Li. He used the rich flow, and later by Daniel Stern and Hubre and Marcus Curry and Dimitri Kazares. They are using those harmonic functions. And recently, now I don't remember those names. I think one of them is Mazzio, 3 Italian mathematicians. They use p-harmonic functions to reprove. And I think their latest work is using p-harmonic function to even prove Riemannian Penrose equality. Okay, and also recently, Pen Miao, he wrote one paper, and he can also use similar ideas, use those harmonic functions to reprove those. Okay, so we have now more than 1, 2, 3, 4, 5, at least 5 ways to prove. Anyway, so this is just a remark. Okay, so now we talk about Riemannian Penrose inequality. Remember, on the positive mass theorem, all the manifolds are complete without boundary. So now when you talk about the boundary, so that you have to compose something, otherwise you might not be able to prove positive mass theorem. Because if you're, for instance, the negative Schwarzschild manifold, so if you just cut them, then you are not complete metric, then you have boundary, or then you do not have this positive mass theorem. Okay? So now for boundaries, and one of the notions we have is just horizon, and then to be more precise, and we need to use those either say outermost minimal surface or outer minimizing minimal surface. Okay, so in the original proof of Christian-Yeoman, they use the outermost minimal surface, and later it's generalized by Bray, okay, to include those outer minimizing. Okay, so basically it's like this. So let's just still draw a picture, okay? So this is one surface, we say sigma. Okay. So if it's outer minimizing, then so any other surface, okay, sigma prime surrounding it, so then your area is greater. So this is quite natural if you are seeing Euclidean space, okay? So if you are bigger than you have, but when you have a matrix, then you need to impose as well. Otherwise you have some neck or something, then you can't do that. Right? Okay, so this is a notation, okay? And it's obvious you just found here that the outermost minimal surface has to be outer minimizing, okay, and actually strict. Okay, so the positive mass Riemannian Penrose inequality proved by Christian-Yeoman, and later or independent by Bray, it says, which I'm quoting here is Bray's theorem. Okay, so if it's asymptotic flat, non-negative scalar curvature, and your boundary is outer minimizing minimal surface, okay, and then you have those ADM mass has a lower bound, which is contributed by the area, okay, in the form like square root of the area over 16 pi. Okay, and moreover, the equality holds if and only if this one is asymmetric to the just Schwarzschild manifold. So this is really a canonical choice. Okay. All right. So this is the theorem. Okay. So now we are talking about PMT with corners. It has a deep connection with quasi-local mass. We'll probably see later. But now I'm have a little bit more notations here. Okay. So basically, you are not talking about one manifold, but two manifolds, but pinched together. Okay. Okay. So basically, I'm saying here. Okay. So you have two parts. Okay, we have two parts. So this is your omega, say G omega. Okay. Okay, so now you have a boundary. So this is partial n, but this is equivalent. Okay, isometric. Okay, so I can see this way. And moreover, your mean curvature. This is your mean curvature, and this is your mean curvature. Okay. So your mean curvature are the same. So here, the metric. Of course, all of them are non-negative scalar curvature. So basically, so if we put them together, you will have this one. Okay. So this one is the metric are the same.
So you're gluing them along values?
Yeah, you can't say glue because your metric, although your metric is the same, right? But that's only only pointwise. You don't say that derivative are the same, right?
Second fundamental.
Yeah, second fundamental don't match at all.
But so you could glue them to have a non-smooth.
You can glue them, but the thing is, if you really glue, then you change your metric, right? If you put them together, the metric is not smooth, right?
Yeah, that's what I said.
Yeah, the metric is not smooth. So
I think that's a dependence on the culture. So in metric geometry, we would say gluing, even without the differentiability.
Okay, so
But in differential geometry, usually they require smoothing also to glue.
Yeah.
Yeah.
Thanks, Christina. So basically here, the most important issue here is second fundamental form. Okay, so you have second fundamental form. They are not, in general, they are not equal. Because the second fundamental form can be considered as a derivative of metric, right? So in here, we don't guarantee they are the same. Okay.
I'm sorry, the H is the theorem of H.
It's a mean curvature. So
what does it mean? The scalar here or that?
Scalar here because it's surface. So here we only impose that the mean curvature have a sign. Okay, then your ADMS is still positive, and moreover, okay, so the moreover, if equality holds, okay, if equality holds, then your metric is C11 diffeomorphic, up to a C11 diffeomorphism to the Euclidean metric, which is a flat metric. Okay, so again, the reason here is that the C11 diffeomorphism, and then basically saying your metric is up to a Lipschitz, right? Your metric is still only Lipschitz. Yeah. So you can't say it's after gluing you are smooth. That's not true. Okay? That's in general not true. Okay. So basically, this is proved by using spin proof by Siyuan 10, and later using gluing and conformal chain by Miao, and then later by McFerrin's Healy using rich flow. So the idea is if now this is actually a very, very good application of rich flow. We know by Miles that Miles-Simon that as long as you have C0, okay, you have C0 metric, then you can run rich flow. So here we actually have a Lipschitz metric, so we can run rich flow. And moreover, Sakihide and McFerrin actually discovered that along this rich flow, your mass is monotonic. So by Miao's proof, you can gluing and doing conformal change, but then after those change, your mass is not monotonic. So you can't prove the rigidity. But here, using rich flows, you can prove the rigidity. So that's the beauty of this McFerrin's Healy's proof, which is a good application of rich flow. Actually, turn out this is a key proof for our rigidity for Riemannian Penrose inequality. So now with PNT, so you can actually has question.
I'm sorry, come back to the previous slide. So what do you mean by corners here? The corner where the
Corner with a hypersurface corner. So basically
I
this is
see.
hypersurface.
Okay.
So this is not smooth around here.
I see.
And is that mass monotonic under the flow or constant?
Monotonic. So, but if you are zero, then monotonic. So you have to be zero. So so that's how they prove rigidity. Okay, so now we actually have another setting. Okay. So now just this is NGN, more or less the same. Okay. Okay. Omega G omega. Okay. I can sigma, right? Okay. So this is sigma H, which is the minimum surface. Okay. So the metric here are the same. G partial n equal to sigma. Okay, so this is auto minimizing minimum. Okay. Should write auto minimizing. So this is auto minimizing. Okay, so basically it's just the same setting, except that also we need to have a mean curvature condition, right? So this is the mean curvature. Yeah. So the same thing. You only need to have a sign on the mean curvature, then you can prove the Riemannian Penrose inequality was called just same stuff. Okay.
Right. So just to understand, even going back to the previous theorem. So from what I infer is that there isn't a general version of the positive mass theorem for manifolds with not very smooth metrics. But you can handle non-smoothnesses of this particular kind where it's across a hypersurface with mean curvature inequality.
Okay, so there's actually a conjecture by Rigidity. So it says if your in a general manifold, right? If you are not smooth, and his conjecture is this. So if your singularity set is codimension 3 or 4, let me see, codimension 3, sorry, codimension 3. So if it's 3 dimension, then if it's dot, if a point, isolated point, then supporting mass theorem holds. Okay, and for 3 dimension, it's actually proved by Charlie and Christos Matolidis. But for high dimension, it's not known. But for like codimension 1, like this, so this is a special case. Then you have to have mean curvature condition. So, but for codimension 2 and others, it's still not really known.
No conjecture.
So for codimension 2, then it's some lines and angles, and this is some Gromov, some dihedral, and some conjectures on there. Okay. For codimension 3 and more, and then that's Rigidity conjecture.
Thanks.
Okay, so this is a very particular setting, and it actually has the application in quasi-local maths, which we'll see later. Okay, so in Miao, this is proved by this theorem. It's proved by Miao and then Koenig. Miao, but in their setting, because they are using those conformal chains, so they cannot prove the rigidity. Okay, so because along those conformal chains, you cannot ensure that your metric, your mass is monotonic. And here, the problem is you cannot directly use rich flow. The reason is you have a boundary. So you can the rich flow with boundary, then you cannot run the rich flow and make the metric on the boundary the same. You can't do that.
You can't keep it.
You can only keep it on the conformal class. That's, I think, proved by Paniatios. Yeah, Paniatios. Yeah, but you cannot make the metric the same. So you can directly use McFerrin's keys idea, okay, directly. Okay, so now I'm saying those things with corners actually has applications quasi local mass. The reason is we just look at those Brown-York mass. Okay, so now Brown-York mass is the following. Okay, so this goes back to the isometric embedding theorem. Okay, so this.
Can't move that much.
Oh. We have another one. The third one. Can you use this? I can use it. I can use this. So basically, Siyuan theorem is like this. So we just draw pictures. Okay, so you have omega, okay, G phi. So you have sigma. So you have induced metric G. Okay. So now, if I'm assuming this is I'm assuming, okay, so your boundary is actually just S2G. Okay, your boundary is just a sphere. Okay, and moreover, I'm assuming in the Gauss curvature, okay, from this metric, the boundary is just positive. So now this setting is just in the first slide, in the second slide, we're talking about isometric embedding. Okay, so now this one naturally, okay, isometric embed to R3 as a convex surface. Okay, so I still denote this. Okay. So now you have another surface. This is in R3, so you have a mean curvature, and we know it's convex, so your mean curvature is positive. Okay. So now in here in Euclidean space, then this is S2, so you have a region outside or inside. Okay, so this outside, I don't need to do this. Okay, later on. Okay. So you have a surface. So now you have two mean curvatures, right? So this is in R3. Okay, this isometric embedding is guaranteed by Nirenberg covariance. Okay, so this is it. Okay, so they are isometric. So you can define this H0 minus H mu G. And this is Brown-York mass. So this is H pi is just constant. Okay, so this is just well defined, just using the symmetric embedding theorem. Okay, so now Siyuan theorem then, okay, in this setting, the Brown-York mass is non-negative and equality holds if and only if this is this region, this omega G, this is asymmetric to actually this here, okay? This the one inside the, okay? So in other words, this can be considered as a quasi-local version of positive mass theorem. What positive mass theorem says, your mass is non-negative and equal to 0 if and only if this is Euclidean space. Here it's just a local version. Okay? Your Brown-York mass is non-negative and equals 0 if and only if it's a region in R3. Okay, so especially when they prove the rigidity, it's actually just using the positive mass theorem with coordinates, just the theorem we just said before. All right, so several years ago, with Miao, we are able to generalize Siyuan theorem to Schwarzschild manifold. Okay, so basically we are saying pretty much the same thing. Okay, so basically, okay, sometimes 2, okay, we're just doing the same thing. Okay, okay, so now this is sigma. Okay, so your mean curvature is positive. All right. So because we are not able to prove the existence theorem, so we assume Okay, so this is isometric to Schwarzschild. So this is too small. So this is sigma. Okay. So this is MM, GM, which is Schwarzschild. Okay. So now you have a HM. Okay. So you can define this left hand side. Okay. So I'm not writing anymore. Okay. So basically, the only difference between Siyuan and Penn and our series, okay. So first of all, we allow those minimal surface here, okay. So they are here. They don't have as a boundary component except the sigma, okay. Second of all, they are asymmetric embedded into R3. So this asymmetric embedded theory is guaranteed by Nuremberg theorem. But here, because there's no such theory exists, okay, even for now. So we assume this embedding exists. Okay. So in particular, if this is very round, which means the perturbation of a coordinate sphere, then this is true by openness of Ln1. Okay. So now the other difference is our left hand side, which is the Brownlow mass in their setting, is different from there, right? So, but if we put m equal to 0, which when m equal to 0, then Schwarzschild manifold is Euclidean space. Then you see they are actually the same. Okay. So now with this one, the left hand side, we can consider this is just a generalized quasi-local mass. Okay. Then this is you have a lower bound, which is given by the area of the mass contributed by the minimal surface. Okay. So at that time, unfortunately, we do not have the rigidity. The reason is again because there's no rigidity of Riemannian Penrose inequality because that's the one we need to use. Okay. Well, but what we can do at that time is we know if the equality holds, then your mean curvature, okay, in the Schwarzschild manifold and your original one is the same. And moreover, the equality holds, then your mass m, because this one mm, they are equal. Okay. So this m is really equal to this. Okay, so that time we know this one. Okay, so now if you have that one, then what do we have is the following. So if we put our setting in the rigidity case, what do we have? We will have the following. This is indeed just MMGM. Okay, and this is your original one, our original one. Omega G omega. We know this sigma, and this is sigma, this is sigma H. Okay, so this is H equal to HM. Okay, and moreover, M equal to the mass contributed by this one. So everything is actually just the setting of Riemannian Penrose inequality with corners. Okay, when you have the equality holds. Okay, I probably write this. Okay. So if the metric are smooth here, then this is just rigidity of Riemannian Penrose inequality. Then you have, this the whole thing is a Riemannian Penrose, Schwarzschild. Okay, but here we only know, okay, the metric is equal here. Okay, so mean curvature is the same. Okay, your mass equal to this one, but we don't know if this thing is really a domain in Schwarzschild. Okay, this one yes. Okay, this one we don't know. So we want to use those information to get this one is indeed the Schwarzschild, like in Euclidean, like the PMT with corners. Okay, so if mass is 0, then this is C11 diffeomorphic to Euclidean, and in particular the unbounded part and the bounded part, both of them are symmetric to part of Euclidean space. Okay. All right, so that's.
Hi, may I ask a question?
Yeah.
Can you go to the previous slide, please?
Yeah.
So you have this like assumption of like this existence of the embedding.
Yeah.
But like, is it known like what conditions like assure such existence or?
Okay, so in a special case, for example, if your metric is very close to a round metric, then yes.
Right.
In general, it's open question.
Ah, okay, thank you.
And it will be very desirable to know the existence in this part because that fulfills all the inequality, right? It does not depend on other assumptions, which is not so neat. Okay. All right. So this is a question is if we can prove that the bounded part is isometric to a domain MFGM. Okay. All right. So now let's just go back to the very beginning. Okay. So very beginning we say, okay, if you have two symmetric surface in a Schwarzschild manifold, okay, we know by Li and Wang's example, you can't expect they are the same thing. But what about with our assumptions here? The mean curvature condition seem to be a natural one. So if we impose a condition on the mean curvature, which is here, okay, then can you prove that they are really asymmetric to really the same one after rigid motion? Okay. So now in the very beginning we say find a natural condition. So here one natural condition, I don't say it's the most natural one. One natural condition comes is the mean curvature condition. Okay, because that's what we do in all those PMT with coordinates, right? So your mean curvature. Okay, so if in that settings, okay, then this fall back actually to the Riemannian Penrose inequality with coordinate because okay, so you have two surfaces. Okay, let's see. Another one. So sigma 2. Okay, so now you can compose. This is sigma 2. So the other part 1. Okay, so this is sigma. Okay. So you can see the the boundary region inside sigma, and you can see the outside region of sigma 2. Okay, you put them together. Okay. So if you consider the mean curvature, then this is now this part is this part is really Schwarzschild, and this part is also Schwarzschild. Okay, but your metric are the same because they are asymmetric on this surface. Okay, and your mean curvature are the same. Okay, so this is exactly the settings in the Riemannian Penrose inequality with corners. Okay, the rigidity case. Okay, so this setting has been studied. Okay, earlier in 2018, one by Li, Miao, and Wang. Okay. Oh, in the Schwarzschild, then it's just a graph over the horizon. Okay, so yeah, your boundary. So basically a graph of S2 or Sn. So now, okay. So now they have proved that if you have two starship, both of them starship. So basically now you're writing this thing as a PD as actually single function, right? So you have two graphs, okay? So you have two functions, and then you have a equation about the asymmetric surface. So your induced metric are the same. So you have one equation, and your mean curvature are the same. You have another equation. So you can play with this. Okay.
So the additional constraints here are the star shapedness and the inequality.
Yeah.
That remove the non.
Yes, that's what they prove. But star shapedness is a little bit too strong. So Bonnie Chen and Xiang Wenzhang, they come up with another proof. Okay, so this only works in R3, in 3 dimensions. So one of them is star-shaped with a non-positive ridge curvature. The other, you don't have star-shapedness. You can be anything as long as your topology is homologous to the horizon. Okay. So this one we always assume that those things are surrounding the horizon. Okay. So you are not expecting that one is surrounding the horizon, the other is not. They are the same. This is not something we expect, right? Okay. So we just shape out topology. So then you can prove this thing. Okay. All right, and because the star-shapedness of linear one theorem works actually for high dimension, and Chen and Zhang theorem works for 3 dimension only. The reason is they need to use existence of asymmetric embedding that only works for 3 dimension. It does not work for high dimension.
Sorry, a little bar.
As ambient ridge curvature of the Schwarzschild. Okay. So it does not. This is actually part of technical assumption in my work with Miao before. So we expect that this condition here can be removed. Okay, so this is only to guarantee the solvability of a certain equation. Okay, but this is quite technical. All right, so this is several years ago. Okay, so what Miao and I proved is that actually in the Riemannian Penrose inequality, okay, in the localized Riemannian Penrose inequality, that's 3-dimensional. This is asymmetric to a domain MGM. So basically, similar to this one, okay, but I guess I removed something there. So if you have the quasi-local mass inequality, the equality holds, then this is just a domain MGM. So then you just really get a rigidity for that part parallel to Schwarzschild theory. Okay, so in the Riemannian Penrose inequality with corner, then Siyuan and Yu, they actually using, okay, so we know if you want to prove such a Penrose inequality, you have 2 proofs, right? One is Huiskin-Yama, the other Bray. Now they have another. Okay, so they just use the inverse mean curvature flow. So you run the inverse mean curvature flow, you know the monotonicity. Right? But the problem for that one is you have a surface outside, so you don't know the inverse mean curvature flow when they touch, right? You cannot, passing through the surface. You cannot run the inverse mean curvature flow passing through the corner surface because your metric is not smooth. Okay, so you can run until after that. So they prove that if your surface is kind of some star-shapedness, they use a unique minimum geodesic, then they can prove only inside one. So inside region is asymmetric to a domain in Schwarzschild manifold, but they cannot say anything really about outside one. Okay, except they are static. Okay, so that's the previous result. So the work with Miao, that's 2 years ago, we proved that first of all, in the Riemannian Penrose inequality with corners, so this is the most, we have 3 motivations. One is asymmetric surface with asymmetric surface. The other is localized Riemannian Penrose inequality. The third one is a Riemannian Penrose inequality. Okay, so just don't want to confuse you. So the most general case is Riemannian Penrose inequality with corners. Then we actually prove that if the equality holds, then you have second fundamental form as the same. Okay, so basically now, and the inside one and outside one both are asymmetric to a domain, a region in Schwarzschild manifold. We do not say they put together is a Schwarzschild because you have to some regularity issue. Because the most expect you can expect is your metric is Lipschitz. You cannot expect high. And the theorem works for 3 dimension to 7, which is same restriction as your
Other counter examples for
nope,
okay, so
but we don't know how to prove. But I think for there's a preprint, I guess, by a student of Rick Shen, because in 8 dimension is special because 8 dimension minimum surface and minimizing isolated singularity. So I think you can prove, but it's only appropriate, I think, is in his thesis. And for more than 8, we don't know. Okay. Hope it's not a counterexample, because for more than 8, then there's a counterexample for for many things, right? Okay, so the query is, okay, how localized Riemannian Penrose inequality works, and isometric surface works if you have mean curvature condition. So also works for expression. Okay, so I'll not really talk about the proof. The proof is basically we just combine Bree's proof, okay, the monotonicity, and with McMaster-Hide's idea. Okay, so instead of running the run the rich flow directly, we first reflect the manifold and do the conformal change. Then after that, your manifold do not have a boundary, but you have potential singularity. But this is a removable singularity, so basically you have a complete manifold. Then you run this McMaster-Hide's rich flow. Then you can do this. Okay. All right. So one question. First of all, the mean curvature condition is actually too strong. The reason is in Euclidean space, isometric surface, convex isometric surface, they are already the same, okay? Or if you just your mean curvatures are the same, okay, and they are the same. So basically, if you are convex and your mean curvature are the same, then there's so many proofs saying they are the same. Okay, so now you need two of them. That's too strong. Okay, although this is not in Euclidean space, but this is too strong. So basically, can you get a weaker condition, for example, integral condition or other things? Okay, and the other thing is this is regarding our RPI. Basically saying because of the non-rigidity, okay, for each embedding, we have this thing is true, right? For each embedding, this is true. But for each embedding, the left-hand side is different because the left-hand side is depending on the embedding. Right? For instance, this one depending on embedding, HM depending on, okay? So those are depending on the embedding. So one common question is, because this is true for all the embedding, so if you take informal, it's also true, okay? But if you take informal, first of all, can the left-hand side can be realized by some embedding, right? We don't know. I guess it's yes, but if that one, then how to characterize, right? So yes, that's another question I asked. Actually interesting is that all of those things, when we talk about asymmetric surface and everything, we always saying this is convex. What if we do not have convexity? So for instance, how to prove that two torus, asymmetric torus, they are the same? Right? It's not convex anymore. Okay.
Not even sphere.
So we can only do sphere. Okay. Okay. That's all I want to say. Thank you.
Question?
I'm not sure if this question is so instead of like Schwarzschild, suppose you have a boundary of say 2 different components that are the same. Similar being so the upper manifold of the boundary with disconnect.
Oh, you mean here or?
Yeah.
Oh, this doesn't really matter. So in our group, it doesn't matter it's connected or not connected. So as long as you have the mean curvature condition and the metric, yes, then you're good.
They wouldn't start here.
So the star-shapedness is so improves the star-shapedness. All those things is not really in use to prove the PMT or RPI. It's more or less to prove those localized Penrose inequality. So it's different.
In your main results,
Yeah.
if you could, you have the upper part is isometric to Schwarzschild region, and the lower part is isometric to a Schwarzschild region.
Yeah.
Do you have a distance preserving one-to-one map from your manifold with corners combining both parts to Schwarzschild?
Oh, the reason we do not write the thing is actually we can see that we have a C11 diffeomorphism to the Schwarzschild manifold.
So it's distance preserving. It's a metric space isometry.
Yeah. So the reason we do not write that way is then you need to write in Gaussian coordinate. Okay? So it's not really.
Yeah, well, that's a coordinate-free notation. I just wanted to emphasize. I knew that was true, and I wanted to emphasize it because there are metric geometers in the audience who just call that an isometry. So you have you have that distance preserving globally. Yes.
Yeah.
Okay, so let's thank the speaker.
Thank you very much.
Your last slide said optimal embedding, and I guess I didn't, in case you're